Hello students, let's go to Module 9, Linear ODE with Variable Coefficients. Up until recently, we have been studying linear ODE with constant coefficients. In fact, we spent quite a bit of time doing that. According to our textbook, chapters 2, 3, and 4 were all about constant coefficients. Yes, we went through a humongously important tool of Laplace transform, but all the applications of Laplace transform we ever dealt with were all about linear ODEs with constant coefficients. Now let's go to variable coefficients. How do they differ? Well, let's see. Here's a general form of the linear ODE with constant coefficients. You can write the same thing using the linear operator form like this. And then how did he handle? Here's a brief review. We take a Laplace transform and break up the left-hand side using the linearity property of L. And then you can use the input derivative formulae, change all these derivatives. And then the right-hand side is a Laplace transform of F, so it becomes capital F. Now we take the like terms together. What do you have? This coefficient part of capital Y, that part is a characteristic polynomial, isn't it? That has degree n, and the other has degree at most n-1. So divide and solve for capital Y. This is what you're going to get. You have R of S over Q of S, which is a proper rational form. And that corresponds to the Laplace transform of the solution of the homogeneous equation. And that one's particular. Here's an example. If you have a function like this, the Laplace transform of the non-homogeneous part, the capital F part, is highlighted in red here. And then decomposed by partial fraction, you're going to get something like this. And then you take the Laplace inversion of each, you're going to get something like that. And the red part, this part corresponds to the non-homogeneous part, highlighted in red. All the others are homogeneous. Color coding would help. This is the kind of thing we had been doing, of course. Now, how about the linear ODEs with variable coefficients? This time, the coefficients an, n-1, an-2, those are no longer coefficients, no longer constants, excuse me. They are coefficients, yes, coefficients, but not constant coefficients. These are variable coefficients now. an of t, so it's an expression of t. an-1 of t, another expression of t, and so on. In that case, how do we handle it? Well, let's apply Laplace transform. So far, so good. And then let's break up. No, we can't. We can't break up like this because we cannot bring out all these coefficient functions out. When they're constants, yes, we could. When they're expression of t, no way. So for constant, we can always bring any constant coefficient, this b, outside of the integral like this. Now what if we have b of t? Can I bring it out like this? No, you can't, because this is an expression of t, and this whole integral is about integration by t. So you can't do this. So it doesn't work. This one doesn't work. So you cannot rely completely upon Laplace transform. Yes, it'll turn out the Laplace transform will help, in some cases at least, but you have to have some completely new angle. One of those new angles is, actually this is not a new angle, this is an old angle. Here's a reminder. We did deal with some variable coefficients before, and that's for the first order. When you had first order, we can start like this, or if you had some leading coefficient function here, divide and make it into standard form like this. And then we can take the integrating factor, antiderivative of this p, make it capital Q, and then e to the q power, that's the integrating factor. And multiplying by the integrating factor, we can combine the left-hand side into a single derivative like this, applying the product rule backward. And then taking the antiderivative, you're going to get the answer. That was the method of integrating factor. We used it for the first order. That's an old angle, but of course we're going to need some new angles as well. What if we have higher order? There are many ways, but one of the ways is reducing the second order to first order. And once you successfully do that, then you can use this. Or sometimes reducing the third order to second order, and then reduce second order again to first order. Do this, and then push it back. More complicated, yes, but you should not forget what we did in the first order case, because it's a cornerstone. Okay, so much for the background, and let's have some example. Let's keep it simple. Let's consider these three functions, y1, y2, and yp, sine of t over t, cosine of t over t, and sine of t. Prove that y1 and y2 satisfy the following homogeneous equation. That's not too difficult. All you have to do is to take the derivatives and then plug those in. To take the derivative, okay, use quotient rule. Second derivative, another quotient rule, so it's gonna be a messy computation, but elementary. Put those in and yes, you're gonna get the solution. How do you do that? Of course, I do not recommend paper and pencil computation because it's elementary but messy. Here's a mathematical command. Indeed, it works out. y1 is this, y2 is that, okay? And then what is this line here? It's the left-hand side of this original ODE for y1. And then ask Mathematica to simplify. Do you get 0? Yes, indeed. Same for y2. Next, how about yp, the one highlighted in red? It's a solution of this non-homogeneous equation. How do you check? Well, this one's actually easier because the derivative is cosine, the second derivative is negative sine, so put everything in there. You can easily check this one. Previously, you had some messy derivative computation, but this isn't too bad. But still, it's too elementary, so I think it's a waste of time. I'll just show you a mathematical command. So define yp as sine of t, and take the left-hand side of that ODE and make it simplify. Do I get the right-hand side? Yes, indeed. I did get 2 cosine of t. By the way, this kind of program works out fine because the right-hand side is simple, so simplification here yields this value. So if the right-hand side is actually also kind of messy form, then you may get some different type of simplification, which is not obviously the same as the right-hand side. In that case, what do? Subtract the right-hand side, and then simplify and see if you get 0. This is a little bit more typical. Left-hand side minus right-hand side, and then simplify. Practice with your Mathematica program. And then prove that this is the solution of the same non-homogeneous equation. Basically, it's a principle of superposition. You can add those up. And the proof is left to the students. It's a messy computation. Elementary but messy. But you can do it a little bit better with computer algebra system. How about solving the initial value problem? Okay, all right. Here we have a general solution, C1 and C2, and we can determine those C1 and C2 using these two equations. Plug in pi, y of pi is 1, so equation number 1, and plug in pi, but you have to take the derivative, and then plug in pi, so we have the equation number 2. 2 equations and 2 unknowns, C1 and C2. Yes, we can solve it. And here's Mathematica's solution. Oops, sorry about that. Here's Mathematica's solution. Define my function. Oh, here in my program, instead of C1 and C2, I use A and B. And then the third line, that's how you solve a system of equations. First equation, y of pi is equals to 1, y prime of pi equals negative 1. We have 2 equations. Solve it with respect to A and B. Okay. What do you get? We get negative 1 and negative pi. Indeed, if you define -1 and -pi as a and b and put those into this form, and you get what you want. This is the left-hand side of that ODE, and minus right-hand side. So you're supposed to get 0, and indeed you got 0. If you want some paper and pencil computation, here you go. Elementary, but I think it's a waste of time. So let's come back to this example. It was a nice example in the sense that we just discussed a linear equation with variable coefficients. We have t expressions here, homogeneous case and non-homogeneous case. Through this example, we verified that similar kind of idea, the linear combination of homogeneous parts, c1y1 plus c2y2, plus the particular, that works as the general solution of the non-homogeneous equation. Indeed, it's going to be the case all the time. We'll prove it, but we saw that, we verified it. And then we went through how to solve the initial value problem if you have IC, initial conditions. But most of all, please note that we had some glaring holes here. How in the world do we find y1, y2, and yp? That's the big question, and that's the question that we'll have to answer in this module. And then the next lesson, lesson 10 as well. How do you get sine of t over t? How do you get cosine of t over t? And then how do you get sine of t for the given, the particular part, the non-homogeneous part? 3 big questions to answer. And all three questions will be answered in Module 10, not here. Okay, before moving on to section 2, let me show you some well-known examples. Bessel's equation, where new value is some constant, typical integers, and those appear whenever you deal with cylinders. And Laguerre equation, I'm not so sure about that. Legendre equation, that appears whenever you deal with spheres. Chebyshev's equation and Hermite's equation, I'm not so sure. I'm not as certain about those. All these are historically important equations, and they all have roots in physics. Some engineering, but mostly physics. Now, let me mention a little bit about the fundamental theorem. I'm not going to prove it, I'll just mention it. A linear ODE has a unique solution under a given initial condition. That's basically what the fundamental theorem is talking about. Here's a little bit longer version. We have unique solution in a certain interval, which we call the interval of definition. So that's a little bit more accurate expression. Why is it so important? Well, consider this kind of situation. You spend a lot of time and money also to find something, but it turns out that you're doing something in a region that there's no solution, or there are infinitely many solutions. So whatever you found, it's just garbage. It doesn't matter how much time or money you spend. Whatever that comes out is garbage. Well, how do you avoid those kind of situations? Theoretically, we have to have a foundation first. That's what this fundamental theorem is all about. For linear ODEs, under given initial condition, we have unique solutions. So always we have a solution. So whatever trick that we learn here is actually valid. We are trying to find a solution that exists. Number 2, it's unique, which means whatever method I use, if I find a solution and that is a solution, I don't have to exhaust all the choices out there. If I find a solution, possible by some lucky guess, that's okay. If I find one, that's a unique solution. That's the basis. Without the basis, nothing actually makes sense. Okay, we are done with section 1, and before moving on to section 2, let's have a little bit of discussion for self-selected students. This is completely optional. How do we prove this fundamental theorem? I'm not going to complete the proof, but I'll show you some steps here. Basically, what we do is to reduce it into first order. How do we do that? this is the nth order, which means the leading coefficient cannot be constantly equal to 0. So you can divide by the leading coefficient an, and then you can solve with respect to the nth derivative. And you can rewrite this original equation into this form because the denominator an is not always 0. And for simplicity, we can rename all these into different characters, okay, like this, all right? So this expression and that expression over there are equivalent. Now, first manipulation is done. From here, let's take the second manipulation. We're going to define functions x0, x1, x2, and so on by the original function y and its first derivative, second derivative, third derivative, and so on, all the way over to n minus first derivative. If I do that, then this original linear ODE, which actually came from this general form, equivalent to that, and equivalently into this form. Let's see. x0 prime is x1, x0 is original, x1 is derivative function, so y prime is y prime. That's basically it. And how about x1 prime is x2? x1 is y prime, so take the derivative from the first derivative. Of course, you're going to get the second derivative. Continue, 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 and last here, n minus first derivative, that's where we start, and take the derivative once more, then I'm going to get the nth derivative. Consequently, we have the right hand side here, and that's what we have over here. So this right hand side corresponds to this final line. Y is x0, y prime is x1, y double prime is x2, and so on. So in the end, we get this reduction. We can express it in this matrix expression like this. This thing and then the derivative, because all these are just primes. And then we have kind of affine expression, matrix times original x plus some constant here, non-homogeneous part. And then I can put those together, all together using the vector expression, where x of t is now a vector function. Now, what did he end up with? We originally started with a single variable function, y of t, and turned it into a vector function, made it more complicated. But the trade-off is, instead of linear ODE of order n, this one is order 1. We only have one derivative here. So we reduced it successfully to a linear ODE of order 1. Now, how about first order ordinary differential equations? Do we have the fundamental theorem there? When do we have unique solution? And that condition is so-called Lifshitz condition. Okay, I give up now here. This is way beyond 3410. I usually cover in real analysis too. And tentatively it is 3610, but soon to be promoted to 4000 level course. And it turns out you can check the Lifshitz condition like this. Oh, never mind. Anyway, for self-selected students, we went through actually the majority of the proof. And the idea was the reduction. So higher order reduced into the first order, and that is the general direction here. Proof goes like this. Also, many of the solutions will go like that as well. So many of the examples here will be second order problem, and we're going to do some work to reduce to the first order, and then we can use the method of integrating factor, and then we're going to be done with it. In practice, we won't have enough time to consider third order, reduce to second order, and then reduce again to first order, and then going back because they can be really tediously long. So mostly we are going to consider second order.